Okay, everybody. This is a recording of the problems that I sent out. I want to apologize for the sort of lack of fidelity of these problems. I am pretty tired and rushed to get these out, and unfortunately, when that happens, multiple errors are made. What I'm going to do here is I'm going to talk through them as I intended them to be, um, and sort of point out various issues that arose, which hopefully will give you a good opportunity to reflect on the various concepts related to some of Chapter 3 and 4. All right. So the first question that I ask you here is, which of the following represents a pair of species in which the first is diamagnetic and the second is paramagnetic? Um, so in the first case, you're looking for something that has all paired electrons, right? So diamagnetic equals all electrons paired, and paramagnetic equals at least one electron unpaired, right? So if we look at these configurations, this was one that I ended up changing because I had accidentally put Na+, which is diamagnetic, and paired it with Cr+, which is indeed paramagnetic. So let's go line by line here. So magnesium, right, it has its outermost electrons paired. All electrons are paired because the electron configuration for magnesium is Ne3s2, and these of course are paired. So that's diamagnetic. That satisfies the criteria that our first one is diamagnetic. But the second one is not paramagnetic because it's calcium, which is right under, which the electron configuration there is argon 4s2, right? And that's also paired. So answer choice A can't be the answer. If we go to the second one, Na and Cr+. Now again, I originally accidentally put Na+. I changed this to Na and then Cr+. Okay, so we have Na, which has an unpaired electron, right? Because Na's electron configuration is what? It is Ne 3s1. This is unpaired, and this is a paramagnetic species, so immediately we can rule out answer choice B. Answer choice C, we have Pb4+. And if we look at Pb, let's look at the neutral elements configuration, right? We have ignore this. Pb should be, if we look over here, we've got xenon, and we've got 6s2. We have 3D. We actually get across the entire, not 3D. We have 3, 4, 5D, 10, and we have 4F 14, right? And then we have 6P 2, right? And the valence electrons that we take here are the outermost ones, right? The 6P first, and then we take these as well, right? So when we take these off, we have something that certainly is diamagnetic, right? Because all the electrons here are paired up, and of course within the core they're also paired up, right? So for Pb4+, all those electrons are paired, so it is indeed diamagnetic. And then silver neutral, if we look at silver neutral, silver has the configuration of krypton, and we have 5s2, 4d9, but remember this is one of the exceptions because it's right below copper, so we rewrite this as krypton 5s1, 4d10, okay? But even still, this has an unpaired electron, right? This is unpaired. So this is paramagnetic. So this satisfies our requirement here. Okay? So let's move on to number 2. And if we look at number 2, we're looking at which of the following rows has the incorrect formula name combination. So what I'm going to do is basically go through this and correct what needs to be corrected as well. Just because here I purposely gave you the wrong name formula combination, right? So NaBrO3, the correct name of this is sodium bromate. Listed it as perbromate. The correct name is bromate, sodium bromate. Okay, so that was an incorrect one. CuNO2, that is copper 2 nitrite, because the charge on copper is 2+ there, all right, not 1. So the name was wrong there as well. So this is an incorrect structure altogether, right? So for iron 3 phosphate, which I give the name of, you would have FePO4, right? Because PO4 is charged 3- and Fe is charged 3+ in this case. So the name would be iron 3 phosphate. Okay? And then finally P2O5, this is actually a molecular compound, and we would write this indeed as diphosphorus pentoxide. Okay? Because again, that nomenclature structure applies when we have molecular compounds in which we have covalent bonding, generally between everything being nonmetals, right? Okay, so the revised correct answer to this is E, which W, X, and Y have some kind of problem with them, right? Which I've now shown you how to solve all of those. Okay, moving on to number 3. Consider the ionization energy in the table. Okay, so look carefully at this. We have the first ionization energy is 1086 kilojoules per mole, right? The next one is 2350. The next one is 4620. The next one is 6220. And then all of a sudden we go 38,000 and 47,261. So how many valence electrons do we think we have? Well, it seems to me like these are all relatively easy to remove compared to these, right? So these are definitely core, and these are definitely valence. So which of the elements is most likely to be described by this? Well, if we think about it, the only one that really makes sense would be carbon, right? So if we look at carbon's electron configuration, we have helium, 2s2, 2p2, right? This is 4 valence electrons, right? This here describes the 1s2 core configuration. Well, guess what? Those 2 electrons are described by these ionization energies, whereas these are the valence electrons, okay? And it's easier to remove those 2 p's first, right? And then the 2 s's, which are lower in energy, become a little bit harder to remove, but not to the point where they're core-like. You can see the core-like electrons have very high ionization energies, right? And to reiterate, we always want to draw an energy level diagram to help us understand this conceptually. Right? And so we have this configuration, right? So these are our valence, and these are down in the core, okay? Core and valence in the case of carbon. Okay? Great. Let's move on to number 4. Number 4 is another one that I didn't write as intended, but we're going to go ahead and solve it basically as though it were open-ended, okay? So kind of ignore my goofy distractor and enter choices there. So how many orbitals can be described by orbitals? Notice we're talking specifically about orbitals by the following combinations of quantum numbers. For scenario I, n equals 3, L equals 1, right? So for this, we have a 3p orbital, right? Or subshell, I should say. So that gives us 3 distinct orientations, -1, 0, +1, correct? So there are 3 possibilities here, or 3 orbitals, I should say. All right, so this is 3 orbitals. And an orbital refers specifically to one of these orientations, right? Of course, you can have spin up and spin down. If we were talking about electrons here, we would say 6, okay? Second one is where I didn't write it as intended, but we can look at this anyway. I actually meant to put L there again, but I put M sub L accidentally, so that was kind of a problem. Or no, what did I mean to do? I actually meant to put M sub S, not L, because I wanted it to be 1. So the answer really was supposed to be A, but I apparently wasn't thinking, but you know, operating off of limited sleep does that sometimes, right? So note to you all, get sleep before your exams. Your brain cannot function without them, right? Without the sleep. So M sub L equals 1. Well, there's a couple of scenarios in which M sub L could equal 1, right? Or actually a few of them. So for n equals 4, correct me if I'm wrong, you can have a 4s, a 4p, a 4d, and a 4f. Now, M sub L equal 1 is impossible for the 4s, right? But it is possible for each of these. Therefore, there are 3 types of orbitals that can involve M sub L equals 1, all right? So, for example, if we were talking about the 4p subshell, we have 0, -1, and +1, we would talk about this orbital. If we were talking about the 4d subshell, 0, +1, +2, -1, -2, we would be talking about this subshell. For F, 1, 2, 3, 4, 5, 6, 7, we would be talking about this subshell, right? Or this specific orbital, I should say, right? Okay, so in this case, we also get 3 orbitals that are possible there. And now scenario 3, n equals 6. Well, this is pretty simple because we know that the number of orbitals that are possible, distinct orientations, right, of orbitals that are possible for any given n is equal to n squared, and so this is 36. And we can look at this individually as well. For n equals 6, what can we have, right? What distinct orientations can we have? We can certainly have a 6s, right? We can have a 6p. We can have a 6d, right? We can have a 6f. Now, if we count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, you notice that that still doesn't account for the 36. Why? Because technically we can have higher and higher virtual states that would never be occupied. Like for our 6G, right? And we can have like a 6, let's see, 4, 5, 4, and 5. Yeah, I think we go up to a 6H, right? And again, now the number of distinct orientations for a G orbital would be 9, so we're going to add 9 to our 16, and then we're going to have to add 11 for the H, right, to that. And so when you sum that all up, when you sum 1 plus 3 plus 5 plus 7 plus 9 plus 11, what we should get out of this is 36 distinct orientations or orbitals, right? Okay? So a correct answer to this, if I had been using my brain a little bit better when writing this up, would be 3, 3, and 36, okay, respectively. All right. Number 5, I wrote that to be actually pretty easy. The only one down there that is a hydrate is the copper sulfate trihydrate. Okay? Dot 3H2O. And what this means is that you have these 3 H2O molecules that are actually trapped within the structure of the copper sulfate here. Okay? So this whole thing here is copper 2 sulfate trihydrate. Okay? Because you have 3 waters trapped in the crystal structure, copper 2 because you have to specify the oxidation state or the charge of the copper here, right? Because it's your transition metal with one that can have variable oxidation states, and sulfate, which is just your sulfate anion, which of course is SO4 2 minus. Okay? Let's go through number 6. Okay. Number 6. Which of the following rows contains compounds that are all ionic? Well, spoiler alert, it actually is just row W. But let's go through this. Sodium sulfate, right? It involves a metal and a polyatomic ion, so we know that this is ionic. And this is the compound, sodium Na2SO4, right? Because Na is +1 in ionic compounds, and then sulfate is 2 minus. Compound 2, CuOH2. That is copper Roman numeral 2 hydroxide, right? So we have our ion, metal ion, and we have the polyatomic ion as well. The one that's going to throw a lot of people off is the ammonium phosphate, NH4 3PO4. So the NH4 plus is a polyatomic ion called ammonium. And PO4 3 minus is phosphate, right? So it's ammonium phosphate. Notice that even though the bonding within these polyatomic ions is covalent, the bonding between them is ionic, right? Because these are both polyatomic ions. They have net charges. So this is indeed an ionic compound. So row W consists of compounds that are all ionic. So what about the others? Row X. Immediately, you know that that's molecular, right? N2O5. And that would be called dinitrogen pentoxide, right? Carbon tetrachloride, also molecular. That's CCl4, right? Manganese 4 oxide is an ionic compound, and that would be written as MnO2, right? Because each O is 2 minus, right? And if you have 2 of them, your manganese would be 4 plus to counteract those negative charges, right? Okay. And then for Y, we have KMnO4. KMnO4 involves an interesting polyatomic ion, which is the permanganate ion. MnO4 minus is the permanganate anion. And then you have a K plus, right? And this is potassium permanganate. That's the name of this compound. CH3CH2OH is ethanol, right? The alcohol in alcoholic beverages. So that's definitely covalent, right? A molecular compound. And then PCl3 is phosphorus trichloride. And that is also covalent, right? That's just straight up between 2 nonmetals, and there's no ions involved whatsoever. All right. And then Z, for row Z, immediately rule it out, P2O5. P2O5 is phosphorus pentaoxide. It's kind of similar in nature to N2O5, right? But it involves phosphorus instead of nitrogen. Keep in mind, phosphorus is in the pnictogen group. It's right below nitrogen, right? So it has similar behavior to nitrogen. BeF2, beryllium fluoride, that is an ionic compound. And then zirconium 4 oxide. So ZrO2 would involve Zr2 4 plus, right? Because each O is 2 minus, kind of like the case with manganese. So this would be called zirconium for oxide. Okay? And that's also ionic, but compound 1 in this case was molecular or covalent. Okay? So let's go on to number 7. All right, so this one involves a little bit of thinking. Which of the following would be expected to have the most negative electron affinity? So the most negative electron affinity arises from a case in which an electron is going to be very, very stable, meaning it's going to find a very low energy level to go to. So for example, if we have some low-lying orbital down here and we have an electron that initially at E equals 0 is not interacting with the nucleus whatsoever, if it can come here and then go down, right, it's going to release a lot of energy, right, to the surroundings. So electron affinities tend to be negative. They're not always negative because there are cases in which if you try to shove an electron in a system that already has too much electron-electron repulsion, not enough protons to pull new electron density toward it, you actually get a positive value for that, and that means that putting it in would require energy to keep it there, right? So it would be an unstable interaction due to high electron-electron repulsion. A good example of this is look up the ionization, or sorry, look up the electron affinity for F minus. It's actually a positive value, okay? So which one would be expected to have the most negative electron affinity? And if we look carefully at these, what we see is that O is probably going to be the correct answer, right? Because first of all, neon and krypton, we can immediately eliminate. These are noble gases. They have full outer subshells, right? So adding an electron to these systems is going to be a little bit difficult, right? Without creating too much excess electron-electron repulsion. Generally, those electron affinities actually are going to be greater than 0, okay? In a positive direction, meaning that they're unstable if you add an additional electron. Br minus, that's isoelectronic with a noble gas, right? So same issue with F minus, sort of, okay? Br minus is a little more polarizable, and that's a little bit of a different story. It has more protons overall, more electron density around it overall, which makes it more polarizable. But this is not going to be a favorable situation to add an additional electron to that, right? Too much electrostatic repulsion. It's already in a configuration isoelectronic with a noble gas. It's fine. Na. So while Na certainly has a spot open for an electron, keep in mind that the effective nuclear charge is actually not that great, right? Effective nuclear charge is not that great for sodium. It's a metal, high in metallic character. A valence electron is relatively loosely held, right? Because we've just gotten past a noble gas configuration. So what happens now? We have a new set of core electrons that are screening out the new electron from seeing the nucleus. So that existing electron is not held very tightly. That 3s orbital is pretty high in energy, okay? And if that 3s orbital is relatively high in energy, there's not going to be a lot of incentive, so to speak, energetically for this electron to come down and end up there, right, to make Na minus or something like that. So that one certainly would not have the most negative electron affinity. But then we go to oxygen, right? And oxygen has relatively low-lying 2p subshell that is not fully occupied, right? It's pretty far to the right on the periodic table. Effective nuclear charge is relatively high, right, due to the fact that we're still filling a given subshell here to 2p, but we keep ratcheting up the nuclear charge as we go along. So here, you could probably make the argument that your electron coming in is going to release a decent amount of energy, right, to go from this vacuum continuum where it's not interacting with anything to interacting with oxygen's positively charged nucleus. Okay, so the answer to this one would be E. It would have the most negative electron affinity. Okay, so let's go on to number 7. Well, number 7 is another one that I did not write in the way that I intended originally. So let me make sure I got my pen up here. I don't. Okay, here we are. So which species is or are argon 3d9 5d1 a valid excited state configuration for? So let's go species by species. So for cobalt, let's write our ground state first, right? For cobalt. Cobalt, we can go and write argon, and then 4s2, and 1, 2, 3, 4, 5, 6, 7, 3d7, right? So we know immediately that we're not going to be able to make an excited state that is, at least not of the neutral atom, that is isoelectronic with, our target here, sorry, I already wrote it, our target here is this. So the number of electrons don't align, right? And we need to make sure the number of the electrons stays constant, but where those electrons are promoted or where they exist is not constant, right? So cobalt is not, it's not valid here, okay? Copper plus, okay. So again, we start initially with our regular configuration. Now remember, copper is an exception where we have 4s1, 3d10, okay? Copper plus, what do we ionize first? We ionize the 4s subshell. So this goes away, right? Now it's interesting because this is the ground state of copper plus, okay? So if I were to draw this in an energy diagram, we have the 3D subshell here. Everything down here is core. And this is actually all filled up, correct? Now, let's say I have some virtual state way up here, 5D. This is the 5D subshell. And I happen to take an electron from here. I happen to put in, let's say, a photon of light whose energy is just enough to take it from here and promote it up to the 5D level. Well, guess what configuration I now have? It's exactly this configuration here. That is a valid excited state configuration for copper plus, 1 plus, okay? So that works out. So let's go to silver, right? For silver plus, okay, we have a similar situation, right? Ag plus, if we start, but now we're down a period, right? So now we go Kr, 5s1, 4d10, or 4d10. So now if we ionize this, what do we take? We take from the s level, right? So this goes away first, and now we've got the correct configuration for this. Now, if I promoted one of these electrons though, right? It went to the 5D subshell. That would be an excited state, but what would the configuration be? The excited state configuration in that case would be 4D9, 5D1. 3D is not the same thing as 4D. So this is not valid. It doesn't work. Okay, and finally zinc. Let's take a look at zinc. Zinc, we have argon 4s2, 3d10, right? And so there's no way that we can recreate this configuration because, again, we have run into the issue of we have too many electrons now in zinc, right? The number of total electrons doesn't match. And again, excited state doesn't mean that you've ionized it, right? You could have an ion. You could talk about the excited state of an ion like we did with copper plus, but the number of electrons is conserved in the system when we're talking about the excited state relative to the ground state, right? Because an excited state is nothing more than moving from one bound state in which the electron is interacting with the nucleus to another bound state in which the electron is still interacting with the nucleus. It's just in a more unstable configuration. Why? In this case, because the electron got promoted up in energy. It's higher in energy overall, therefore the whole thing is less stable, okay? So let's go to number 9. Oof, almost getting there. Number 9. Rank the following ionic compounds in terms of increasing magnitude, absolute value of lattice energy. So here what we can do is for E lattice, we can invoke Coulomb's law, right? We can say basically that E lattice can be computed roughly by saying we've got some proportionality constant times Q1, Q2 over the distance between the two ions. So in this case, we're talking about these are the charges on the ions, and this is the relative distance right? So in this entire series, the first thing that you should notice is that the charges on the ions are always +1 and -1, right? You always have a plus charge and a minus charge. So the entire numerator remains invariant. Numerator is invariant, i.e. it doesn't change. What changes is the distance between ions, so we have to use an ionic size argument, right? So let's think about this. The lattice energy is, the magnitude of the lattice energy is inversely, right, proportional to the distance between the ions. So if the ions are very small and they can get close together, this is small, and that makes the magnitude of the lattice energy actually pretty big, and then vice versa. So for the greatest magnitude, all right, we would expect it to be the smallest ions here, right? So the first one that jumps out at us for the smallest ions is LiF, right? Lithium and fluorine are both relatively small, okay? Fluorine, in fact, is fluoride, I should say, because it's an ion. F minus is very contracted. Lithium plus is also very contracted. They're both isoelectronic with neon, okay? And so they're going to be able to get pretty close together, and therefore the strength of that interaction is going to be quite strong. So it's going to release a lot of energy if you take an Li plus and an F minus that are in the vacuum continuum and put them together and let them interact and form a bond, right? A lot of energy is going to get released, and that's the lattice energy there. Okay, so this would be the greatest lattice energy. Now let's go to the least. So this is our greatest. I'll put LiF over here. So greatest. And I'm going to call this a magnitude. I'm going to absolute value it because remember, we have a negative sign here. So again, these lattice energies are negative values intrinsically. So we have to keep track of this based on, like, let's say magnitude, right? So let's see which ones are the largest ions, and they're going to therefore be far away from each other. Well, all we have to do is go down in the periodic table, and we see cesium iodide, right? Both are big and bulky. They're going to be relatively far away from each other, so the strength of interaction is not as great. So if you took a cesium ion and an iodide ion in a vacuum and then put them together, they're not going to release as much energy as LiF when it forms, okay? And then we got the intermediate cases. So we have Ki and NaCl to compare. So Ki is probably next up, right? Because I is fairly big and K is certainly bigger than Na. I minus is bigger than Cl, right? And K plus is bigger than Na plus. So that leaves NaCl over here, okay? So if we look at this, our answer is C, okay? And this one, apparently I did not screw up when I wrote, so that is very good. And then finally, let's look at number 10 here, okay? Which of the following species would contain 3 dots in the Lewis dot structure representation? So let's think carefully about what Lewis dot structure means. Lewis dot structure only takes into account the valence electrons, right? The outermost electrons that are available for bonding. So if we look at I, our Lewis dot structure is going to be equal to, we're going to have 5, okay? Right, 5 valence electrons, because why? Because the electron configuration of nitrogen is helium, core, 2s2, 2p3, right? So these are our 5 valence electrons. Let's go to lithium. Lithium has 3 electrons overall, but its configuration is 2s1, right? So we have lithium, and that has just 1 valence electron, okay, right here. And then finally, or no, not finally, we have boron. Now boron, if you look carefully, the configuration is helium 2s2, 2p1, right? So we have a total of 3 valence electrons, and here's our winner, right? So Now, we could represent the electrons as paired, but one of the things that we'll learn is that boron can actually create 3 bonds. So you get things like BH3 or BF3. So a lot of times it's going to be convenient for us to write our dot structure out like this, right, for boron. And then finally, we have aluminum 3 plus. Now, aluminum 3 plus is isoelectronic with neon, right? So if we wrote that, we would just write it like this. There are no more valence electrons, right? Okay. So again, thank you for your patience with me. Hopefully my talk through of what I was intending here with these problems made sense. I wish you the best going forward with these problems and other problems that you're using to study for your exam. And